All right. Good morning. Good morning. Do I need to throw the ball?
No, experimentation.
Okay. So this is the last day, hopefully, but we are full of events. That doesn't mean that I am tired, okay? But we have a lot of events again, full of like great talks. And then this is the third keynote today, which is another great talk. Hopefully you will enjoy. And it is my pleasure actually to introduce Professor Dario Rossi joining us from Huawei Paris Research Center. He has multiple positions there. He's the director of the AI for NetLab and the director of the DataCom department there. He has a PhD from Politecnico di Torino. Before Huawei, he was part of Department of Computer Science and Networking in Telecom Paris Tech, as well as electrical engineering at Politecnico di Torino. He was a visiting researcher in UC Berkeley as well. He has 20 patents, more than 200 papers, and more than 10 awards, including the Google Faculty Research Awards. So with that, I would like to welcome him for his presentation. I'm sorry.
Yeah. Thanks a lot for the introduction. Thanks a lot for the invitation. Really happy to be here. I was here actually from the first day. I enjoyed the conference. Didn't get the chance to talk to all of you. Just for one thing you missed is that I also participated in LCN in 2010, so 15 years ago. Was much younger then, so still enjoyed. And the talk I was in 2010 was something that Anja was talking about in the first keynote, so about fairness and congestion control. So I'm still happy to see that BBR and Google are making this, reviving this topic. But today we're gonna have a different one. Okay, so that's me. You probably cannot picture, not from 2010, but so this one is the topic we're going to be talking today. I'm going to be talking about foundational specialized models for cyber defense. It's going to be clear what are these models later on. We'll start briefly by going into the AI roots, then profiting of the time to quickly flash to you about what are all the other activities we're doing, so the ones that are not covered in this talk, and then dive into the matter. Of course, there is a lot of people that we need to thank. I mean, I'm here telling you a story, but the story wouldn't exist if there were no people working on it. And the story starts from a galaxy far away. Well, I just want to really provide a really brief account. So here, the main message is that for any new technological shift, there's been a breakthrough. And the breakthrough many years ago was fire. Then we had first revolution. So first revolution with steam, with electricity. And electricity was first used to make goods. But then we started finding different usage of electricity. For instance, we moved from assembly line to having ability to program logical controllers, so moving, electricity signals and bits. These bits can also move far away, so we can have a network that helps digitalizing all our information in the world. We recognize that with signals, we can also program devices to do complex operation, and some of these operations are simply similar to the one that we have in our brain. Now, what I want to focus on is these three latest areas in which, funny enough, in 2016, 17, 18, we got ACM Turing Award for major breakthrough in these different fields. And as already was pointed out during this conference, Backpropagation won the Nobel Award 2 days ago. And yesterday, actually, we had AlphaFold winning another Nobel Award in biology. So really, I'm excited to talk about these things because these are inventions of the 21st century that are already being credited with, that are being credited in this, and they will even move forward. So let's start considering what was in 2010, which seems like many years ago, but actually it's 15 years ago. I was in LCN back then. What were the people doing in AI? So there have been a number of theoretical advances, massive amount of volume of labeled data, especially labeled at the time, and massive amount of compute that made it possible to have the first breakthrough of convolutional neural network. So if you remember, we were 2012, we have AlexNet, 60 million weight. It seemed huge at the time. So what are we witnessing now in 2010 and 2020? So 1 decade passed. we still have back propagation. So it's not by no chance that, it just won the Nobel Prize. True, we have also other architectures, no longer convolutional. Transformer has supplanted everything. We're going to talk about transformers today. But I want you to put the attention on the massive increase in terms of volume level data. So we went from, ImageNet to Lion 5V, so 5,000 time increase, essentially infinite number of labels. You have a description for every picture. And massive amount of compute, because what we consider to be large, 60 million parameter, now it's more on trillion that you count, and months of training for $100 million. So for $1 million right now, 100 million is going to be the next generation of models. In this context, what we're doing in my lab is that we're looking at artificial intelligence, where there are multiple branches. We are active in these branches. We are using different methods. And typically where we start, given that we are also AI for net lab, we start from a network use case. And well, the network use case will gonna drive what are the methods that are most up to it. In this picture, I'm showing just the kind of innovation that we do in the open settings, so meaning papers, publications, and we sit across two fields. We sit in the AI community, and we have also a foot in the network community. So we're in interaction in these two type of things. So we do either theoretical work or applied one. Today, we're going to dive in this box, which is basically how we can use LLMs, and not only for security. So we're going to go from shallow natural language processing model to deeper and bigger models in the course of the talk. So now we are at the agenda of the talk. So in the beginning, what I wanted to do was, well, okay, let's take NLP and LLM, the whole field, and the whole evolution, do a cross product with what happens in security, and let's make a keynote in 1 hour. It's not possible. So we all agree that, yeah, that was not a good idea. So I revised it by saying, okay, let's focus on what are some of the interesting things some of the interesting method that makes sense. So we filter these. We're also going to extract a subset of interesting use case of application. We're going to talk about NARCnets, honeypots, and firewalls. And yeah, maybe we fit 1 hour. And actually, it's no longer 1 hour because it was already talking. So, and I want to leave some time for questioning. So, okay, let's see what we can do in this time. So what are the techniques of NLP that are going to be of interest? So here I'm showing what happened since 2010 and before. We were also discussing earlier with somebody about TF-IDF, statistical approaches. It was basically the state of the art from the 50s until 2010. Then things started happening with shallow models for embeddings, then bidirectional STM sequence-to-sequence model. And then attention came in 2017, and we started having transformer models that went from 100 million parameters to 100 billion in just under 5 years. So embarrassingly parallel scaling made it possible to go from recurrent network to something that just has potential for infinite scaling, and there's an appetite for that. So right now, companies are building nuclear reactors, companies are reviving nuclear reactors to power even bigger models. One of the questions that I'm going to have in this talk later, and we're going to use this dichotomy of specializers versus large models, is how big is the model that we need? Now, we can put this barrier anywhere we want. Of course, technological advances will allow us to put the barrier higher because the hardware is going to be faster to compute. So I'm going to put it there close to whenever you say under 100 million parameter, it's a specialized model. And if you're above, if you're on the billion parameter scale, that is going to be a foundational one. We've been using already this technique in the past for different use cases, but the one that we're going to be talking about today, span the wall vertical. So we're going to go from very shallow ones to very big ones. We're going to apply this technique to a set of use cases of interest. And I was really counting on Angie to talk about network telescope. She actually talked about network meta telescope. So you already know what it is. Essentially, it's a network that you can reach, but it has no service. And so why the heck traffic should reach that network? So that's unsolicited traffic. You can leverage that to understand, to do some cyber threat intelligence, to leverage this information to construct information about malicious actor in the network. The second use case is one step further. So honeypot, meaning that essentially now we will put a honeypot to lure malicious actor to engage with us. So because as soon as they engage, we will know something more. We will know their intention, what they want to do, and so we can further exploit that to build cyber intelligence information. So honeypot acts as a decoy service, but they are not critical services. Finally, we're going to discuss about defending a network which has critical important services that are, for which there's either important data or business value that you want to protect. And so you will want to filter these actors as early as possible. So this is the set of papers from which I'm going to cherry pick some of the information I want to share with you. So with that, I think that maybe we can be fit in the 35 minutes or so that are left. Just one precision about specialized versus large models. So this is not something that you find typically. So I want just to comment on the fact that we have a dichotomy. On the one hand, we have the specialized model that have very narrow capabilities. So we're going to typically have a model per task. If your task is darknet, you're going to use a specific model. If your task is intent recognition for honeypot or early traffic detection for firewall, you will need to build a specialized model. But these models are easy to fine-tune, they're not very costly, and they're going to also have excellent performance exactly in the task, the downstream task that you have designed them for. On the other hand, you have models like there where I'm showing one of the Huawei ones, Pangu, based 78 billion parameter. They've been trained on much more richer data. They've read product documentation, they've read all the books, they can speak natural language, they know the API of the product. But so they have generic capabilities. They can trigger an API, they can talk to you. At the same time, they're super costly to train. So we're not going to be able to do a pre-training from scratch anytime we want. And so that's a cost that we need to factor in when we think about it. The way in which we like to think about these models is a cooperation of them. So you see there, we already have a number of ML models that are deployed, and we don't want to trash them and redo everything with a bigger model. So we need to have the model which is, the bigger one, to think about is smaller brother and how to use them and how to cooperate with them. So we're going to see that the cooperation of agents later on. And this is just, if you want to open the box, this is a typical architecture as a compact one, because on the your left-hand side, you have a specialized model based on BERT, so transformer-based architecture with a set of attention and feed-forward layer, number of layer, which is variable here. I'm just showing one for the sake of simplicity. And embedding dimension, of course, I'm showing 3, but the models are going to be on the order of 700 more. And then foundational model, which have a different type of architecture. This one is a mixture of experts. The important thing that I want you to notice is that in the foundational model, you're going to be able to exploit multiple modalities. So whatever modality you're going to have into that, thanks to the first dense layer that are universal, you're going to be able to process this data, whereas typically in the specialized model, some of them are still going to be able to process different type of data, but they're going to be excelling only for the data you prepared. So you need to pre-train and fine-tune them essentially. So let's start from the first use case. Here, as I was saying, okay, you receive unsolicited traffic. And so this unsolicited traffic, you can build cyber threat intelligence information. You essentially have the IP address of the attacker, so which is the sender IP port. You also have the target IP port. You don't want that to be public, otherwise the bad actors will know that you have a telescope someplace. So these need to be kept business secret for obvious reason. But you also receive what is the backscatter traffic, meaning some normal users that are attacked and they're going to be participating in an attack. And so their address is going to be exposed, which of course for GDPR reason is extremely private information. I also want to punctualize that we're talking about dark nets, but not dark web. This is a misconception that many people can fall into. Hopefully with the talk by Angel, it should be clear. Darknet for me is just a synonym for telescope, okay? So we're just gonna use this information. So I'm gonna quickly run through this workflow just to show what are the type of things you can do in the context of darknets. So you have a number of, so here is 1/24 darknet. Just looking at typical 10 days, you have 250,000 senders, so not high volume, that was already pretty clear. And what you're going to do is that you're going to filter some definition of traffic. In this case, we're slicing traffic by considering a subset of ports. So either by looking at a single port, but it's just naive, or by a set of ports defined by an expert, or by a port that are automatically inferred. And this is going to have an impact on the way in which you build sequences. So there were other work that we're doing word embedding for, even for darknets, like for instance, Dante. In that case, they were slicing traffic between given receiver and sender pair. So essentially, they were looking at a sequence of ports. When we do the opposite, we look at a subset of ports, and we're going to look at the sequence of senders that are going to be happening in your network. And what you're going to do is that you're going to be do an embedding of an IP address by looking who are the guys that contacted me before and who are the guys that are going to be contacting later. So I'm going to provide a point in the space, defining an IP depending on who are his neighbors with respect to the point of observation. Doing so will make it the model scale. And I mean, then for the downstream task, of course, then you need to verify whether this makes sense or not. And so you really need to collect some ground truth. If you collect some ground truth, that is kind of costly to collect, but it's feasible for a subset of the traffic you see, you're going to be able to do, for instance, a classic supervised job. And in this case, for instance, taking the top 10, you can see that not only it's scalable, but it's also accurate. When you train on the first 30 days, and then you see what happens in the next day to see if you can recognize the traffic, it is pretty good, unless when it doesn't work. And I want also to show what are the limits. So for instance, one of the limits is that we are trying to build sequences. And if one of the sender has a pattern that is seemingly randomly choosing the different sequences that are going to hit to you, then you're not going to be able to extract much information out of noise. So these are some of the limits. But once you sort of start trusting the classifier, because you have done this job with supervised ground truth, you can start doing clustering. I'm not going to enter how do we do the clustering. The space is big, so you cannot just do k-means and hope to have something working. Actually, this is one real picture of the blob. The magenta or pink purple blob is Mirai botnet, so a lot of devices that you can find there. And what I want to point the attention to is one thing that we discovered through the data. So we had to do the clustering, then look into the cluster and say, what is this cluster? Right? So we don't have ground truth in this case. So we found that that was a 0-day Android debugging worm that was spreading. And actually that was announced in late March. So we had no clue what we were looking at. But you can see that in the data, it started appearing at the very beginning of March. So you can see that there's a pattern of activity that can be spotted automatically. And then some expert need to figure out what it is, but that can be a useful mechanism to do very early detection. Of course, I mean, this is the first preliminary study, but if you want to put this in operation forever, you need to keep training. So what we did next was to basically have an iterative version of it, training, doing a full training on the first day and then doing iteratively for the next month. I mean, that's some ingenuity, not only engineering, but then in the engineering part, we were also able to make it much faster to train so that we can scale it and it's still operational now. Second thing that it's important is that now we have business intelligence collected from one darknet, but and it was very useful to have the meta telescope from NJ. Remember that there are a bunch of darknet you can see from an IXP. But not all XP sees exactly the same subset. Not the same sender are going to target everybody in exactly the same sequence. So the sequence that I learned in a network are going to be different from the sequence that I learned in another network. So we need to realign this, and we did it for instance, between two different networks in two parts of the globe. Or when you have a honeypot that is already in place and then is attacked, you have a sequence of attackers. How can we port that to embedding of another darknet? And so on. So that's more involved. So it's something that but it's possible to do. And one of the advantages is that if you are able to do an alignment, then you will not need to collect the ground truth of each of these networks. And you will still be able to keep the ground truth secret. So a provider can keep this ground truth and just provide then a classification head to different customers. So this is something that is useful. Now it's in this picture, you see already a small b, so it's a nice moment to transition toward the honeypots. where the scenario is slightly different, because right now we want the attacker to hit us. And so what we're gonna receive is direct attempts of connection. Some of the connection are gonna be useful. Whenever the connection is gonna be useful because we have low interaction honeypots like Teapot or Cori, then what we're gonna see is session of attacks like the one shown there. So right now we no longer have only the IP address. We also have much richer information, which is the type of attack. We can say that it is akin to natural language. We learn programming courses, and they are taught to us in natural language. It's human-invented syntax. Can also be binary, but it's still going to be a language respecting some syntax. But it's much more complex and rich than what we saw before. So we need to move from embeddings to transformer attention. And I will also point out one important reason why what is the benefit of moving to more complex models. So now the setting is the following. You have this, you collect logs of this attack, and you want to try to figure out what the heck the attacker is trying to do. And you want to do that automatically, because even if you have a few 100,000 sessions per month, still you don't want to spend all your time looking at the screen and trying to figure out. So what we're going to do is that we are going to be using name identity recognition, so a token level classification, that has the job of saying for each token in the text, token is a sub-portion of the words, depending on the dictionary you chopped. You're going to need to specify which is the intent of the attacker according to the classic Mitra classification. And once you do so, you will also be able to attack, so to track evolution of the attack. I'm not going to talk about this later part, but I'm just going to show how you do, for instance, this for intent classification for a single attack. So right now we are going to be moving to bidirectional encoding representation for transformers, so BERT. It has been pre-trained with significantly larger amount of volume data. You see there 3 billion pairs of words, essentially from book and Wikipedia, which probably are not telling you how to attack every website in the world. They're going to contain some, but it's not specific for that. The task is masked language modeling, so you hide part of the tokens, and then you need to figure out which is this token with this kind of parameter, and the size of the model at the end is on the order of 100 million parameter. So in order to adapt it to our use case, what we need to do is two things. One is we need to do domain adaptation. So for that, we need to essentially take a data set like NLP to Bash that are going to help you moving closer to the domain you expect. You're not going to be reading MOOCs, you're going to be reading attacks. And what I want to point out is the number of sessions that you need to perform the domain adaptation is much, much smaller than the amount of data, volume of token pairs that you need to do pre-training. So we move from billions to a few thousands. So that becomes manageable. And so we need to do two things. One, to adapt the domain in the input, and second, fine-tune in the output, because we want to have an existing set of example representative attack that we take from the one data set, to fine-tune the model to recognize the specific intents. And then we're going to use two different data set, completely different period of time, completely different moments, and position in the network to do the testing. And this is the type of things that the model will tell you. If you receive that string, then you're going to chop it into tokens. When you see a dash, a hash is the start of the next token that splits the current word. So for instance, AP table there, it seems split into two separate tokens. And then for each token, you're going to have a classification of the intent. So one is, for instance, impact, and the other is execution. And in this case, once you have the token level, you can aggregate consecutive tokens to have sort of an idea of what is the predominant type of attack. What I want to make as an example of why word embedding is different than transformer is the following one. So consider myself, I'm out in the street under a tree, and I'm talking about a cat / a dog. It's clear to you that I'm talking about a pet. But if I'm in this room and I'm telling to somebody, hey, cat / dog, maybe he's going to think about, you need to see the content of a file named dog in the root folder of, okay? The words are exactly the same. And a simple embedding model would not be able to make difference between this. While in case of transformer, you can have that, let's take echo, right? So just something that is used to repeat or write on the terminal. It is used, for instance, for discovery or persistence. Execution is most of the time. But you see that depending on the different context, so who are the neighboring words, the intention that the attacker uses in that specific command may differ. And this is exactly one of the real benefit of this more advanced transformer technologies, looking at the tension and the context. All right, so right now we went through the first two use cases. So we're gonna devote a little more time for the last one, where our intention is essentially to block as early as possible bad actors to do harm. In this case, we're gonna have not only the header, but we're also gonna see payload, and some of these protocols are binary, actually. So it can be blob of text or blob of bytes. The task is going to be to divide whether the traffic is malicious or not. In the case whether the attack is malicious, we want also to have an indication of what is the severity level. Why is it so? Because there was a paper in Newsnick a couple of years ago that says that 99% of the alarms are false positive and human time is precious. So if you are sending a trove of false alarm to a human, the human will simply stop caring. They will not see what's good, what's important. And in some of the cases, one of the biggest cybersecurity threats that was hitting target was due to indeed an alarm that was a legitimate alarm that people would not consider because you're too busy looking and wandering through a lot of alarms. So what we do want to do is that for most of the cases, whether the alarms are true, but they are not so problematic, we might be able to handle them automatically, or if they are benign, where they are safe to ignore. And so we want to trigger the attention of the human only on the problems which are of interest. We're also going to have additionally some evidence. We don't just want, hey, it's a problem. Sure, but where do I start looking? So you need to provide me evidence so as I can understand why the machine learning model has taken a given decision. And so this is something that I'm going to show you next. The data we get is from the real system. We have a number of firewalls that are deployed in different customers. These are sending information to the cloud for further processing. We already have machine learning models that are assigning a level of severity to the different alarms. And then operators human are doing as a job daily looking into these alarms. And some of the alarms are going to be de-escalated, for instance. So the severity level that the machine learning model has given us is going to be changed and altered by the human. So we don't have sensors in all this process. We have the data set at the end. And so we're going to be able to essentially try to learn how the human would relabel and so try to prioritize better the alarms that are important to him. In terms of model of interest, here we're going to my role is chief AI expert, but I can also take the hat of chief AI skeptic. I don't want just to use LLM because it's fancy. I want to use the right tool for the right problem. So one of the first questions we were asking is, well, what if you just use the FIDF, bag of words, with classic machine learning? So we need to put a benchmark that is really state-of-the-art benchmark to show if there is any improvement in these more advanced transformer techniques. These ones are much more easy. So in terms of cost, it makes much more sense to use a simpler model. So we're going to be using 50 models with different parameterization. Then we're going to use BERT and families. BERT was known to be severely undertrained. So there's been a number of work later, like Roberta, and then people already adopted domain adaptation for secure BERT, for instance, about security, Unix coder about coding. So both models can be relevant. We're also going to use bigger model like GPT-2 family, up to 1 billion, and Mistral up to 7 billion for just doing the classification task. Then we're also using vector databases. Don't have much time right now. I'm going to discuss the data a bit later. And then we go also all the way down to look at big models, including models that you can run locally, so that you don't need to go to OpenAI. As well as for limited subset of data, we will get clearance to anonymize it and leverage GPT-3.5 and GPT-4 to get information from the cloud. But that, of course, it's a more liability problem because you will need to send data out to the cloud, while for every other processing, you're able to do it in the lab. We're going to have 3 questions in mind, right? So am I out of the job already? Right? Everybody is saying LLM is going to eat all your jobs. So if LLM can solve my problem, I can go fishing. So we wanted to see if I could go fishing tomorrow or not. And I'm not good at fishing. So I really hope that I could do something. Then the second question is, do we have a statistical advantage if you use this model with respect to, I mean, using ML and TF-IDF? And the third one is, okay, now if you want to do things right, you have a lot of choice. What is the right choice that you should make? So here is the task is indeed assess the severity level. Now we have, we're gonna use a smaller set of 2.5 million events. We have 2.5K types of attacks. So these are the attacks that happen in the 6 months we were looking at. We know much more attacks. We are at 30,000 types, but these are the ones that are occurring more often. And we want to categorize in 5 levels. And one of the things that we did is to simply ask, okay, look, this is the log, this is the payload. Please Llama, please GPT-4, or also other models, but for the sake of space, they are not reported. Are you able to put in one of the 5 categories? We're not going with few shot or more advanced techniques. I'm going to comment that later. But if you want to make it very simple, just prompting, would it work? Actually, what happens is that people were showing this kind of confusion matrices early, right? And when you're in an academic event and you're going to show a confusion metric, you're going to show a perfect diagonal, right? This is what you would want. It turns out that in this case, these models are a little bit too overprotective. So they're going to say, oh, it's an attack. It's an attack. You should care about it. And actually, they are going to generate a lot of false alarms. And it also has a cost because computation time is pretty long. So this is not something that you would want to do. So we need to do something different. I intentionally put the picture very small because I don't want to worry with numbers. The numbers are in the paper. But the idea is that we were able to do a systematic comparison to assess whether there was a statistically significant level of difference between bag of words, which is just looking at the set, versus looking at the context, which is what I was showing you with transformer. And yes, there is some amount of syntax that emerge that is captured with the nonlinear transformation transformers that is providing you about 5%. We can assess whether 5% is enough or not. But again, what I want to show you is when does the technique do not work. So for instance, here, typically what we would do in the lab is that you would do a stratified selection. You're going to sample a number of samples, and we are already doing few shots. If you consider the training, you have 17,000 examples, but you have 2.5K, so 2,500 types. We're going to be using between 5 and 10 examples per class type. So these are not many shots. And we are going to test on much larger. So we don't do a 80-20 split. We do exactly the reverse. We're going to train on few as possible and test on larger. And depending on how do you do the splits, if you do stratified, you're going to sample from the future. And that's very good. But what happens in practice is that attack campaigns that you see in the wild are going to be short-lived. So people are going to try to exploit something for a couple of months, and then a new attack will come out. So what happens if with the 2 split in 1508 and 2108 is that there's an attack campaign that you can see a 0-day bomb, something going up in some day in August, very sharp. So if you stop the model training just before that, you will not have no knowledge of that attack coming. And that attack is coming at 37K and 57K attacks per month in August and September. So if you don't have any evidence of that, then you're simply gonna fail to assess the correct level of classification. You might say that it's a 0-day attack, but you have no clue in which category to put. However, if you are able to see even few samples, we have already shown that with stratified, you need few samples. If you have few days, just 1 week, then the performance are like in the stratified case. So just to say that, yeah, there are still problems. Even if you have benefits, you still need to take care of how to do things for use in production and not in the lab, which is one of the good things of being in a company that pushes you to really try to think what are the things that go wrong after you solve or you think you solve the problem. Here I'm showing the table, but I'm going to hide part of it because I just want to give one message, which is, right now we went from using shallow models from random forest on bag of words to use bigger models of 100 million parameter, but we can scale this up. So in this case, for instance, we are fine-tuning GPT models of the GPT family. So either same size of BERT, there are 2 different type of approach, encode only versus encode decode. So can have a difference. And then going bigger and bigger to go into Mistral level, which is 7 billion. And in this case, what you can see I mean, we were doing it on a slightly smaller scale because it costs too much to do this kind of ablation studies. But the idea for us was to test, are the model big enough? And what the picture tells you is that, yeah, the models are big enough. You're not gaining by just increasing the model size, because the model that is 110 million parameter has already all the parameter space you need to do the discrete classification task. Actually, you can also do distillation, so you can make the model smaller. So large enough is what you need for your task. So you don't need just to go bigger, because that's what people are doing. So I want to show how specialized model and the larger one can be useful cooperating together. So in this case, like before, we are not doing intent recognition on the word. So here what we are showing is that we are doing back propagation on the classification task and go see which are the tokens that were most useful to provide a given answer. And for instance, I have three different examples from three different levels. The first one is red alert. I think that people in the room can see that somebody is trying to access a passwd, so a password file. It's a bad attack because they should access shadow file, but anyway, they're trying to access extrude information. And they're trying to do it by doing a classic directory traversal. You see // it means that I'm going to the root folder of the web server. And then what I'm trying to do is that I'm trying to, go someplace else. What I find interesting in this example is that the BERT is learning that, oh, that's something that is important. So it's directory traversal. But it's not important how many paths I'm traversing. This is a specific example, right? So already the indication that I'm stepping out of the root server of the folder is a problem. And then passwd, oh my God. Maybe because many attackers were trying to get that. So this is something that we got by looking at the result of the data. The second one was also an example that was intriguing, because I don't know if you are investing on cryptocurrency. I hope you're not, but if you are doing, you probably know what is Binance, is a crypto network. So a DNS request, because that's a DNS request, you have one query, one answer for domain name called www.binance.com. Why should it be a problem? And actually, it turns out that we were not able to find the answer until somebody posted the reason why. And it turns out that the attacker were using the Binance cryptocurrency network to store malware in the blockchain, so that it never can be turned down. So basically, you have essentially a free storage where you put your malware and nobody can turn it down. Otherwise, they will need to remove the whole blockchain. So that was a vector of attack, which was kind of intriguing and we learned it from by examining the data. And the last one is an example of ZGRAB. I have altered the IP address. ZGRAB is a scanner based on ZMAP. Also, Anja talked about it. So something that you find, okay, people are going to do reconnaissance. It's not a big attack. Anyway, it's already gone, so you cannot do anything. So on level 3, don't do nothing. So this is what you can do by a small model looking at current incident. Now, for some of these attacks, it's not so easy to go and find and understand what the model is telling you, right? Even for the second one, it took several time and reading some books and reading some posts. So these are not something that is meant directly to the user. It's meant to, as a hint, to a larger model that is going to have access to much more constraint, so much more data. So here, the BERT model is going to have 512 tokens, so very small, looking at a portion of packets. Or possibly you can pod multiple packets and have multiple of this analysis. But the logs are much longer. So we have logs, we have CTI information about the sender and the receiver. There's also past incident, model output. So what we're doing is that we are feeding all of those different modalities, including the results and the output from the smaller model to the larger model to get a current incident explanation, which you can get then in natural language, and that can make much more sense. And we found that the cooperation of the two is quite nice, because the small models are going to be pertinent to make the rank level. And second thing is also they're going to be pertinent in giving the right clues so where to look at. So there are a couple of techniques to extract important keywords, and we are currently experiencing on what is the best in practice. So right now, the summary so far is, if you want to extract behavior from something which is not language, then shallow models are enough. And NLP is still useful as a technique. If you want to go a bit further, so right now you have languages, then yeah, these techniques are really useful to be able to understand words and their context. And finally, yeah, I mean, we have a range of tools, but we just not need to go too big because we need to find the right size for the right task. But I want to go a little step further. So what is the road ahead? So what are we currently working on? For reason of time, again, I'm going to skip something. So I'm going to try to focus only on two things. So one is retrieval augmented generation, and the second one is multi-agent debates. So if you already heard about retrieval augmented generation, essentially, it's going to try to solve one of the problems that we said before. So these models are large, are very nice. They're going to be talking natural language, embedding language, but they're super costly to train. So given that new attacks information comes out every day, what do I have to do? I mean, do I need to keep training the models forever? It's going to be super costly and difficult to manage. So we want to have, on the one hand, access to domain expert knowledge that is easily accessible, and we want to make that accessible to a pre-trained frozen model. So we can take the benefit of something that is being pre-trained with everything, understand natural language, and then is able to fetch relevant information for the query at hand. So how does it happen is that the human makes a query. The query is embedded. You're going to look for the embedding into a vector database, which has been populated with relevant information, and is going to find the top K by using cosine similarity distance. People were using it early yesterday to find relevant things in different settings, right? So you're going to do a proximity similarity match of embeddings. You're going to find values associated with those keys. You're going to put them in the prompt. And so the language model now has access to a database of information that might be useful to answer this question. So this is how one vector database could look like. We're using now, so these example payloads, but can be multimodal, so no problem. You're going to have, at training time, you're going to have a set of payloads that you're going to be using with an embedding function. Essentially, embedding functions are another deep learning model. So more or less same size of BERT, so under million parameter. They've been fine-tuned to do sentence embeddings. So having essentially a short summary on a space which is 768 typically or smaller in size. And this is going to be your key for searching. So to that key, you can put whatever value you want. And what we're doing is that we are basically converting the database. We already have the knowledge bases that we have from Huawei that knows like 30,000 type of attacks. They already have the remedies. They have examples of problems. And we use that as knowledge that the LLM is going to be able to retrieve when it's going to do a top K query in the vector database. And we are currently experimenting with different type of embeddings, like the one listed there. What is going to be inside the document is what I didn't want to talk about earlier. So before we were doing zero shot. So we're asking the question, here's the payload, tell me what is the level of attack. And it's very difficult to answer that, we know. You can do better. So you know that there are a few shot learning. So we can provide, for instance, few examples. And this attack is of this level, and this attack is of this level. Problem is that there are so many attacks, like 30,000, that it's difficult to find the relevant attacks. So a few shots would probably exhaust the context window of the LLM. So there are other techniques like chain of thoughts, graph of thoughts that are more useful. They basically force the model to build a series of reasoning steps to provide the answer. And this is the path we're going to be following. But instead of providing a generic one, we're going to provide one that is specific to the problem at hand by embedding the chain of thoughts directly in natural language in the database when we search. So that, for instance, this is one snapshot of when you're looking for a given payload. Payload is there on the left-hand side and bottom. You're going to project that in a space. You're going to find top K. The top K is telling you for 1, 2, 3, 4, 5. Well, we have all the 5 examples are from the same category. So in that case, you might not even need to go, to an LLM. But if you want, you have, okay, we have these attacks. So we're leveraging this information. And the key is returned like a data frame. So where you have many fields related to this attack that you can use in the prompt in a structured manner. This is another case where we have the ground truth. It's Microsoft's SMB, CVE, information disclosure. It's also the most similar, it's the top one. But you see the top 2 is a different kind of attack. So always related to Microsoft Windows Samba problem, but not exactly, you don't know exactly which one. And in that case, by just looking at cosine similarity, it's a big shot to say, yeah, I know what is the attack. So in this case, what you're going to be doing is instead to leverage multi-agent debates. So you can think of it like you have a problem in the lab. And what you do is that you're going to ask an expert. But the expert is not necessarily going to be able to solve it alone in the first shot. So you might be having two experts discussing. And what we're doing here is that through the RAG vector database, we are going to find what are the plausible explanations. We're going to have one agent thinking about one possible hypothesis, another one in another hypothesis, develop their own hypothesis separately, then exchange these hypotheses. Another agent also thought that, blah, blah. And then think about whether his hypothesis holds or is better than the second one. Have a resolution step in which they agree on a single answer so that the single answer is passed to a human. Of course, this takes a little bit more time than just having a single shot, but it's still, below minutes level, which means that it's faster than a human going and fishing all through this information, and the human can still do it. I'm just showing an example of so here is the prompt book. I don't think you can read, but one of the main messages that you can template these things, and you have way to access the information. Whenever you see a slash, then you're going to be able to access the information that is found through the RAG database, so augmented, and you can explicitly mention the queries of others, the answers, so to construct a structured discussion between the agents. Okay, so finally, it turns out that if I look at the watch, was not too bad in terms of time, meaning that, yeah, we finally made it to below 1 hour and leave it some time for questioning. So I just want to bring some messages. So I could have actually put more content. I don't know if you would be alive at the end of the talk, but so just, to make a recap. So in terms of technical things that we were seeing today, we're seeing a span, right? And I think that you all know Occam Razor. I just know the old Latin version, so I'm not going to show it off by saying it in Latin. But the main thing is that, you don't need to use bigger model than needed. So you don't need to shoot a mosquito with a cannon. So this is a paraphrase of the Occam Razor. So we're saying that shallow models are fine if you're looking at sequences that are not strongly typed into natural or synthetic language. But that if you have such language and you have a problem with that, then better than bag of words, just looking at signatures, you would need to look in the context, because the meaning of a word can change in the context. And this is what makes a transformer powerful. Finally, if your problems are bigger and bigger, you might decide to decouple and have specialized models solving very specific tasks, and then having a bigger model come in when the tasks become more difficult. So how to arrange the continuum is, of course, something that is not fully solved in this talk. Same time, there's also a tremendous progress in the field. Still quite some work remains. So I was not able to show you much about explainability, but this is one of the bigger problems. Models are a black box. You're going to get an answer. When the answer is wrong, you don't know why it's wrong. When the answer is correct, how do you know you can trust it? We come from a world of products in which things must work 100% of the time. So, or you think that they work 100% of the time. So people are not able to step into a statistical world of explainability, of the model works like this in practice. And in this case, I'm looking at, I don't know. Also, many of the explainability models are using surrogate models. So they're explaining not what your model did, but they're explaining what a simpler model would tell you. So they're not really tied to the dynamics of the understanding. If you think about even the small model I was talking about today, so there are 100 million parameters. So looking at what is really that tells you that you're confident and that you can build trust in the answer of the model, this is something that is still that we're working on. No, we're not the only one, of course, but it's an important area. Additionally, you are all aware of GDPR, and I think that most of you are aware of AI Act. So this is upcoming also in terms of regulation and audit. So this is going to be mandatory. So now the amount of funding in AI is going to shift from adoption also to compliance. So this is one step that is going to be anyway needed. In terms of large language model, we have a problem of grounding. So from time to time, the model is going to give you an answer or cite things that don't exist. They are just statistically plausible, but they are not really existing in the real world. So that's where, for instance, retrieval augmented generation come into play. You can have example and quote this example, but it's not enough. So it can reduce hallucination, but not eliminate. And the other thing is that we have seen in terms of generalization, there's still a long way to go. So there are bits and pieces, but of course, that's a bigger problem. I was talking about training, and when we do training, we are really bound by CPU, GPU time. So right now, we have access to GPUs, but everybody wants to have GPUs. And if your training workflow is big, we have internal conflict, even the team, I need to do my training first. So what are we also working on is going beyond few shots and backpropagation. Backpropagation is useful, still going to be there, but if you, for every sample, every batch, you're going to need to touch all the 100 million parameter of the model, that's probably not the most useful thing to do. So what we're doing is that we're doing investigating technique for sparse training by touching only few of the nodes that would make the most impact. Another hidden elephant in the room is that once you're going to have these models, you're not going to keep training them forever, but you're going to be using them in the inference a lot, and that's going to consume a lot of energy. So right now, for instance, that we were going to bigger models, I didn't show, but we also tried to go smaller models with distillation, and it turns out that you can have for same performance five times smaller model, and 5 times is a lot. So I think that people should also focus into not only 99% accuracy, but yeah, what is the accuracy per joule, accuracy per amount of power that you're using to basically contribute less to global warming, because when we are training this model, we are generating a lot of energy and CO2. So when people are telling me, oh, we can do green AI with, so green network with AI, tend to be skeptical about, yeah, did you also factor in the amount of computation time that it requires for you to get the network to an efficient point? Then finally, data benchmarks are a problem. One of these things I mentioned, we published, I mean, it's going to be published in Connect, but the data set is proprietary for obvious reasons. There are a lot of information that is either business sensitive, like all the data from the cyber threat intelligence, versus data that is private, IP addresses. There might be protocols that are sharing addresses. There are binary protocols you don't know that there's an address, so it's very difficult to share. At the same time, this was also something that was in the question in the previous talks. The data set that are available to the academic community, so people are still using KDD 99, right? So it is not the same kind of playground. So I think that we definitely need to have academia access to a more complex playground. And the playground is not only the data, but also the benchmark. I was showing you, if you do certified selection, everything will work. Job done, paper accepted, can go home, present. But then will not work in the real world, because the real world, next day, we're going to be another attack. So the benchmark is also providing you the way to avoid having data contamination, data leaks that are going to make the problem look similar or simpler. So all of that is not something that we can solve in a day. We're also trying to basically leverage LLMs in order to build the data set of attacks that we can share with the public, because we're attacking ourselves. And in that case, the IP address, we own it. It's private addresses. There's no customer involved. There's no human involved. But scaling up this collection to have a meaningful set of 30,000 alarms, 30,000 types of alarm, is some kind of community level type of work. So with that, I think I'm talked about most of the things that I wanted to give you today. So I would like to thank you for giving me this opportunity, for listening, and now I'm open to take any question if you have any.
No worries. Cool. Thanks for the great questions. Yeah. Ready.
Thank you for the great talk. With the use of LLMs, I see two challenges. I wanted to get your opinions on them. One is, like you mentioned, there are very limited number of LLMs because of the resources that it takes to train them. So I wonder whether adapting them makes security measures more transparent to hackers, meaning they can say, if I can beat OpenAI's models on my own, I can probably beat, Huawei's security measure, right? That's one option. The other concern I have is, obviously these models are also available to hackers. So I wonder if that changes the game in terms of securing the networks against them, because you are probably training some malicious models with your
I mean, great
actions,
question,
right?
yeah.
So even a an attack that is labeled as the lowest priority may actually provide a signal to that other model. So I wonder if there are ways to combat against them by confusing the models or something.
So for the first question, actually there are quite a wide range of models, and something that is going to be always secret recipe is how you use them. So the fact that the people are going to be using an existing model doesn't mean that the attacker know how you're going to be using the model. So unless he really has access to much more information, the fact that people are using LM is like saying, oh, you're using SVM or using random forest TF-IDF. I don't think that's a problem. That will not make the attacker particularly more informed. Then I agree with you that it's still a catch and mouse game. So people have started also using LMs to generate automatical attacks. What I've seen is that right now they're not tremendously successful. For instance, only GPT-4 was able to succeed in 5 attacks and giving him sufficient number of time and resources. It was still impressive because he's able to attack this website. So you need to find what was essentially all around cross-site scripting and injection. So that is the way in which I see that LLMs can be used as a weapon, can be weaponized, to automate and scale the type of attacks and so on. That is where can provide difficulty. See, there are a lot of bounty programs, right? So many of the things that are going to be in that space is if LLMs are able to find the 0 day, then they are worth a lot in terms of security, right? Bounty program are paying a lot, and this is generally done with a lot of cautious work. If they are able to find 0 day, they are able both for the attacker and the defender, right? So whoever's going to get the model first, and OpenAI right now released one preview, but they already have one. So if they wanted to use it to find bugs in Microsoft, they would just step up the ability to defend, and then GPT-4 will not be able to attack. So I don't think that arm race is going to be just fought and have a penchant for one or the other, because again, how are you going to be using it? There are going to be other creative ways of use that you don't think about, that the other side will think about it. And when it's known, then we're going to go and unless we have AGI, and then.
Right. Another question. Nobody? You guys are very nice.
Morning, thanks for the talk. Just a quick question. There was a paper at Houston Security 2022, do's and don'ts for machine learning in network security. I think you also had some similar aspects, right? But they questioned using AI techniques, including LLMs for this because of base rate fallacy. Because
actually, I mean, I get the paper. In the Connex paper, we are doing a quite due diligence by citing precisely what are the don'ts that you avoid by doing that. For instance, indeed, the data snooping in the future is the one that I was referring to with the stratified split, etc. They're not questioning LLMs. They're questioning more AI in general, but it's because the security community and even our internal one, they're not necessarily, I mean, they don't have a strong feeling for changing a set of rules that they build with expertise accumulated over time, with replacing them with something new. And I take the point, which is why what I'm saying is that you see that these are tools that need to facilitate the life of human, right? So we are taking the human into account, because when the human clicks that no, the machine was wrong, then it's part of the active learning that we are embedding to do. So that paper is good, but it's not rocket science in the sense that it's basically exposing to the security community things that are pretty well known in the ML community, like avoid data lab. So we go quite in detail for some of them in the Connex one. I didn't talk about it. So just for the start, right? So yeah, we are aware. Okay, we explicitly cite. Then I don't know if you had a more provocative question or
So I think one of the issues is that on the one hand, you have the things you pointed out, that there are issues well known for the ML things like you need balanced data and so on. But I think one of the problems we have in networks is that attacks are a really small fraction of this. So you have a really small fraction, and by this you have an inherent unbalanced data set. And so how do you deal with this imbalances that you also have in the data set, but that are also there in the real world, right? So attacks are still a very small fraction of the general packs that we're having.
So I also have hidden slides. I mean, I was talking about weighted accuracy. I was thinking that people would tell me, why don't you share your data set? So I also had a slide saying that we share the data, but this one we can't. In this one, for instance, this is the type of imbalance we see. Unique event names. We have 2,500 exactly in this data set we extracted. You see that the top 10 roughly represent 30%, right? So if you're just gonna be good with the top one attack, you're gonna already win 6%. So the way in which we do, for instance, is to use weighted accuracy so that the attacks which are really small, we have another imbalances in the class label. The attacks is a fraction which is smaller than 1%, right? And we want to be precisely good at that. So we can either have recollect one, or we can have weighted accuracy, so that all the huge tail of false alarm is not going to be weighted more than the other. So yeah, I mean, there are a number of things we are well aware that the downstream task is help the operator and not just get a paper accepted with 99% accuracy. So which you would incur definitely, because you see all over the place there's these plans.
Okay, thank you.
Thank you very much. Very interesting stuff. I have two questions. One is about the offensive LLM. I assume you're doing sort of passive LLMs, just looking at data, analyzing the data. But in case of, for instance, honeypots, you need to sometimes engage with the attacker. So are you considering those cases in your research, like using them to engage in the best way so that they can
Very, very good question. So actually, we did that with the honeypots. So I mean, we don't want to do pen tests, automatic pen testing, for instance. So that's not our field. I was saying that we're considering this in order for automating the creation of a data set to be released, because it removes the human in the loop. But otherwise, what we were trying to do was to have sort of, I mean, we're doing this 3 years ago, and now I would have done differently. So with the hindsight. But the way in which we were trying to engage was to try to lengthen the engagement with the honeypot. So some of these low interaction honeypots are just going to return bad things. The author is going to recognize that it's a honeypot and then trash it. So we started having interactive honeypots in which you could generate a Docker container, people could interact. And then we also started generating plausible answers, so to keep engaging and have more intelligence. So we did that part indeed on automating the interaction. We did not do cyber offense. Indeed, the title of the talk was about cyber defense. There's a value involved, but we're not enough people to be able to, and we especially are not security guys, so we don't have the expertise and skill set. We're more ML guys. So yeah, I mean, I particularly see there's quite some active things also from the malicious actors. Some of the tools are limited, but there's a set of people that are definitely working on the area. So it's quite active.
Thank you. The second question is about the management or overhead of maintaining these models. So considering a modest IT company, what would be the cost of selecting the model, preparing the data, training it, maintaining the parameters, and continuously updating? So is this plausible for an IT company, or it's an overkill?
Depends on how big you are, right? So I just want unrelated, because it's not for the big models, but when we started, sorry, there are too many slides, so probably I should have went there. Okay. So just to say that, when we were using the techniques, even for the word embeddings, right? So there are some of these which it needs more than 10 days, and then we stop them because they were not just finishing. Something that takes hours, and then something that, you can engineer in such a way that at some point incrementally maintaining it doesn't cost much, right? This precisely something you can do. Same thing for the bigger models. I was telling you that lately we are on the distillation phase, right? So to make it, yeah, sure, it can work, but you need to find the right balance between first make it work and then engineering all the way down to let's make it more manageable. Right now, indeed, we like specialized model because, I mean, on the one hand, they provide exactly the answer to your problem and not just talking, right, which is interesting for the human, but not necessarily useful. And on this one, yeah, there's no additional cost. The real cost could have been, you know, what is how many humans you have in the company that are doing research on that? That cost is bigger than training right now. So right now that we have tooling of this kind, computational aspect is not the primary one. It primes only when you want indeed to make the next generation of Pangu 200 billion. Then in that case, that's a company-wide effort and so on. It's a different story. But for this smaller model, that's not really not a concern.
Just maybe one more quick question. Over there. Okay.
Thanks. Maybe just like a more overall question for someone who is working a lot with AI. I mean, most AI models and LLMs, they're like pretty much out in the open for everyone to use, be it regular user or also attackers. Whereas when you look at law enforcement, they have to uphold the regulations of the countries of the EU, like Datenschutzgrundverordnung, as we have in Germany. There's like pretty much very strict in terms of privacy.
Yeah.
Whereas, you know, like the other side is attacker having all the rights and the other ones restricted. Like, how is your stance on that? And
so, but I mean, let me make it clear. Let me try to go one slide where I have the necessary names. So there are most of the models. Okay, maybe this one. So there are two lines, especially for the LLM, Llama 2 Mistral, and then the second line, which is GPT 3.5, GPT 4. Now, the Llama 2 Mistral, it's open weight model. They're not open source, means that you can download the model locally, and if you have GPUs, you can use them, right? There's now Llama 3, there's QTI. I mean, France is very active in producing these models. So this one, they run on premise. That's a big difference so everybody can use them if they have the resources. GPT 3.5 and GPT 4, you need to go using the OpenAI API. We are also using Claude from Anthropic, Claude Sonnet 3.5. There's Google Gemini Pro, there's Pangu. So we can use the different ones. But if you were an attacker, would you really, you know, go and you need to pay your API with, and you're not paying Bitcoin, right? You're paying with dollars. So would you say, okay, dude, what is your intended use case? Well, I'm an attacker and I want to get money by doing scam, because then OpenAI will have all the transactions. So I don't see that big difference in the sense that the models that are locally, essentially what they're going to do is that you're going to have GDPR in place that you anyway need to do. So you need to have the data legitimacy, data retention policy, data usage. And then on top of that, you need to be able to explain how to use the model, which is something that was validated this year. So there's still going to be some time in order to understand exactly how to do that. But that's a part of the normalization that is helping these parts. This is just adding some, you know, administrative steps for a company that their other people don't need to do. The attacker don't need to have a lawyer saying, how do you respect the law? But technically speaking, there's not going to be a really differentiator. There might be risk associated with how you process the data, so processing it locally, etc. But when you go to cloud models, yeah, I mean, you can, but you're also giving way to OpenAI to recognize that you're using it for not. So that could be a way for Copilot, for instance, to have ideas on who are the attackers and how I want to use it. So I don't think that that's an advantage only for the attacker. And on the other side, in our company, we have a lot of people that are legal, so they're also going to do that work. It's not going to be only the research that are going to be doing it. So they need to have the right level of abstraction to understand this thing is going to happen. So you're just not going to do whatever you want with the data. But then luckily, we are not be the one that are going to be spending their time in red taping, etc. So this month or last month, I was in a workshop where only 2 engineers and the other guys were the legal ones discussing exactly this type of questions. The most difficult thing is interaction because we don't speak the same language, right? So an LLM may help us discussing between engineers and lawyers, but the intent is that one. And then kept working for 1 month. I stopped thinking about that problem and go back to the technical one. So I don't think it's going to be really so tough. It's not an advantage only for the others.
All
I'm
right.
wrong. I hope I'm not.
Good. Well, yeah, we are a little bit over already. Well, let's thank our speaker once again. And then we have a small video for you. And we also just want to remind you, as other speakers, you were here, you know that, but
Yeah.
you can submit paper next year as an author. You have a free registration.
And acceptance rate is higher. I mean, everybody was making a joke, so I figured I had to make a joke.
26%, right? Okay. And with that, yeah, we will be starting the next session at 10:30. We have a coffee break now. And just a reminder, that will be an introduction of next year's LCN. And there will be also a special track in the other room. But we want the attendees of the other session be here at 10:30. Just listen to the 10-minute invitation to the next year's, then go there. Okay. Thanks for that. So I will see you at 10:30 here. Once again.